And our final speaker in the composition section is Dr. Maria Russo, who's based here in Cambridge with NCAS. And she's going to talk to us about the impact of the North Atlantic Oscillation on North Atlantic composition.
Thank you, Alex.
You've had 12 minutes.
Brilliant. This work is in progress and is in collaboration with NCO. They provided us with some of their satellite data. So this is one of the nice thing about ACSIS, one of the useful collaborations that I've found. So I will focus on this talk on the interannual variability of ozone in the North Atlantic and how this is affected by the circulation and variability in the North Atlantic. So this first slide shows the two different phases of the NAO, the positive phase and the negative phase. And this shows that there are large differences in atmospheric circulation, precipitation, temperatures. So the NAO really drives variability in the North Atlantic, or is a good statistic for variability in the North Atlantic. And on the right-hand side, you can see that the NAO index is used as a measure of the NAO, and it can be calculated in a variety of ways, but they all show very similar temporal evolution. So what we're trying to do, sorry, that seems to be one missing. Okay, what we're trying to do with this talk or with this work is try and understand what is the impact of the atmospheric circulation into the North Atlantic, and in particular whether the correlation that you find between the ozone and the North Atlantic is the same across the vertical structure of the atmosphere, or whether it's different at different heights. And in order to answer these questions, I'm going to use a number of observations and model simulations. The observations are at different vertical levels. So we've got surface, lower troposphere, full troposphere, and lower stratosphere. And our model simulations are with the UKCA model. I believe this is the same version that is currently used in UK ESM. And the things to note in terms of model simulations is that we use model dynamics nudged towards era interim reanalysis. So this makes the comparison to observations a bit more significant. And also we're going to use some idealized traces that will help to diagnose transport in the model. So let's start at the surface. And these plots are taken from a paper by Posata et al. In 2012. And they show correlation between surface ozone anomalies at some European monitoring stations and the NAO for the period 1990 to 2005. And as you can see, there's a strong positive correlation between surface ozone in Northwest Europe and the NAO. So next we look at the models. So the first panel here is a model simulation from the same paper. They use the Eckham-Hammonds model, and they find in their model a correlation which is positive. So these are correlation coefficient, a positive correlation as in the observation between Northwest Europe and the NAO, and some negative correlation north of that in the northern part of the North Atlantic domain. So we've done similar analysis with our UKCA model, and we find a similar correlation coefficient between the surface ozone and the NAO. And if we want to understand what is the impact of this correlation onto the actual ozone, we can use this plot on the right, which shows you the percentage difference in surface ozone when you have a positive phase of the NAO compared to a negative phase. So this tells you that when the NAO is in a positive phase, you get surface ozone in Europe up to 20% higher than when you have the NAO in a negative phase. So the question then is, why does that happen? And in order to understand that, we think this is due to the fact that when the NAO is in its positive phase, this leads to increased transport of pollutants from the US. In order to prove that that is indeed the case, we use some surface emissions of an idealized tracer from the US, and we see how these responds to different phases of the NAO. So what we do is we look at the surface traces from the US, And we see that when the NAO is in its positive phase, you get an increase to up to 20–40% in Northwest Europe. And because the US is obviously a large source of ozone, nitrogen oxide, CO and VOCs, this could explain the increase in ozone in the Northwest region in the North Atlantic that we see in the observations and in model simulations. So we think this could be a possible mechanism. So we've done the surface. Next is the stratosphere. So let's try and work through these one at a time. The top row is observations from the OMI satellite. This shows correlation to the NAO, and this shows percentage difference, so the impact of the correlation on this lower stratospheric ozone. These show lower stratosphere between 12 and 21 kilometers, and these gray areas at the north end of the domain are points for which there's very few observations, so we don't really know what's happening there from the observation. If we look at our models sampled in the same vertical slice, so between 12 and 21 kilometer, we see that there's a very similar pattern of negative correlation between stratospheric ozone and this sector of the North Atlantic going from Northwest Europe all the way to the northern part of the US, and there's a positive correlation in the southern part of the domain. The impact is kind of similar again in terms of that sector of the North Atlantic, although the model seems to have a larger impact. And also there's this larger blob that the observations don't show. So we can then extend this information with our model and say, okay, this is what happens in the lowest stratosphere, but what happens in the full stratosphere from the tropopause to the top of the model. So we see that the signal is still there, but it's much reduced in magnitude. So this suggests that the driver of this signal originates in the lowest stratosphere, but it's got an impact on the full stratosphere. So the reason then is, why does that happen? And in order to explain that, we can look at a paper that came out in GRL in 2000 by Appenzeller. And what they found is that the surface pressure influences tropopause pressure. And they showed a correlation plot between tropopause pressure and the NAO. And you can see that, when the surface pressure is low, the tropopause becomes lower. And when the surface pressure is high, the tropopause becomes higher. So this also has an impact, not just on the tropopause pressure, but also on the stratospheric ozone. So if your tropopause goes down, you've got a larger stratospheric column, so you get a maximum, a local maximum in stratospheric ozone. And when your surface pressure is high, you get a lower stratospheric column, or a shallower stratospheric column, and therefore you have a local minimum in your stratospheric ozone. So we believe this pattern that we see here drives the correlation between the stratospheric ozone and the NAO, and it's in fact quite similar to what we find here with the positive, negative, positive in the models and partly in the observations. So far so good. We've, both for the surface and stratosphere, we found that the models and the observations agree, and we found plausible mechanism for why the correlation exists between the ozone and the NAO. Next is what happens in the troposphere, and this is a bit more complicated because tropospheric ozone column is influenced by multiple processes, including stratosphere to troposphere transport, STT, boundary layer venting, precipitation, lightning, and so on. And observation are also more uncertain in the troposphere. So what happens then? So again, the top row here shows observations. For the troposphere, we have two different observations for the troposphere. The OMI shows the surface to 6 kilometers, a lower troposphere, and the OMI minus MLS shows the full tropospheric column. But they both agree in having this kind of negative correlation between ozone and the NAO in this sort of sector of the North Atlantic, and a positive correlation lower down. And this is a non-negligible impact on tropospheric ozone column, with, you know, parts of Europe and all these regions having a decrease in tropospheric ozone column up to 20% with the positive NAO phase. So what happens in the model? well, as you can see, the model does not look anywhere near like what the observations show. The signal in Europe is the opposite, and the magnitude. So difference and the observation, the impact, and we looked at some of them, and we still need to look at some. But one of them seems to shed light impact the NAO on the stratosphere. The regional scale is linked to lines, and we know that the strength and the location of latitudes vary with the fauna. In order to 3F, this is the ozone transport into the troposphere through this SDT transformism. So integrate this O3S over the troposphere, and we got on the right shows exactly that. So this is the tropospheric column of ozone that has been transported from the stratosphere, and this is the observed correlation of tropospheric ozone with the NAO. So the patterns here are a lot more similar, and you can see a kind of negative plus a positive and a negative in the middle, which doesn't explain everything, but it looks a lot closer to the observations. So this suggests, at least initially, that the observed correlation pattern between the tropospheric ozone and the NAO could be driven by STT and how the STT responds to different phases of the NAO. And I mean, there's obviously a lot more work that needs to be done there and a lot more analysis, but that's one of the things that we are following up at the moment. Okay, conclusions. So for the surface, the observation and the models agree. There's an increased transport of pollutant from the US. We think this is the main mechanism to Europe during the positive phase of the NAO. There's an impact on European background ozone of up to 20% higher during a positive NAO phase. This could be, could have repercussions for quality. And in the stratosphere, similarly, the observations and the models support the existence of a tribal structure in stratospheric ozone, which is associated to these large-scale changes in tropopause with the NAO. The impact in that case is a lower stratospheric ozone in Europe during positive NAO, which could lead to increased UV exposure. And in the troposphere, I think, model and satellite show different correlation pattern between the North Atlantic ozone and the NAO. And the observed correlation seems to broadly match the model correlation between the stratospheric transport of ozone and the NAO, suggesting that stratosphere to troposphere transport might play a role in determining the observed tropospheric ozone response to NAO. And obviously more work in progress, so we'll probably hear more. Thank you.
Okay, number of questions. Scott?
I was just wondering, so you found this connection with increased ozone in NAO. I'm just thinking during winter time, during say blocking events, the blocking may be associated with the other side of things, and the side. And during those times, there would be quiescence, things would be relatively, the circulation would be weakened over certain parts. And if you're over a city like London, there's a lot of pollution coming up, and so you may, strangely enough, get increased ozone that goes against this sort of paradigm. I'm just wondering whether, if you look at, distributions of these things, whether maybe in NAO might, think of NAO got longer tails, but perhaps portray this the circulation which you do blocking perhaps. And perhaps this is much of the story, but not all the story of these connections.
Yeah, sorry, I think it's a bit hard to summarize the question. It's more like a general point. Yeah.
Can you anticipate the effects of blocking with what you just said?
Right, yeah, okay. So the main, so can you anticipate the effect of blocking on the surface ozone impact of NAO? So, I mean, in this case, we've not really looked at that. And obviously, this is a winter month analysis where ozone is normally not as high as it would be in the summer. So it would be interesting to repeat that in the summer months. Although in the summer, the ozone production of ozone, I think, becomes much larger, and we expect that the photochemistry will prevail against, you know, in comparison to transport. So that might be a different story in the summer anyway. So, you know, this is just to say what might happen, but I'm not really wanting to say too much more about the impact on air quality in London, if that makes sense.
Ken?
I guess it'd be fairly easy to repeat that for aerosol.
Sorry, you say this is easy to repeat the analysis for aerosol. No, we've not done that. So I've done that for ozone, and I've started doing it for CO, and obviously for all the idealized traces that are there. I think our expertise is really not in aerosol, but if you're interested in something like that, I could help in doing that. And, you know, it should be fairly easy to do that for aerosols, yeah.
And then final.
Yes, so this was this winter time correlation.
This is all wintertime correlations, yeah.
Then, I guess, in the stratosphere at least, then you have these, you sometimes have these sudden warmings, stratosphere sudden warmings in the North Pole, which really map really strongly onto the and they also put a lot of ozone around. So do you think that maybe there's some pathway where these warmings are determining this ozone distribution and then having an effect on the NAO, and you just look at the ozone?
Yeah, so the question is whether the stratospheric sudden warmings can impact the NAO and be responsible for the stratospheric ozone response. And I think this is a possibility. So to a first stage, I've just looked at the correlation between the NAO, what forces the NAO, then, you know, there's loads of things that go into that, but that is obviously a possibility, yes.
All right, thank you very much, Maria, for bringing talk.